Just confirm me once whether my voice is audible or not. Just confirm me once. My voice is audible to you? Just confirm once whether my voice is audible or not. Okay. So, a very good evening, everyone. Myself, Prateek Mishra, and I welcome you to the YouTube platform of IMS GATE Academy. We are conducting this series for the most expected concept in environmental engineering for GATE 2024. We already did sessions. We did sessions on alkalinity and hardness and other important topics. Here I have listed one of the important topics that you should read in environmental engineering with more focus. Extraction of groundwater, well hydraulics, alkalinity and hardness. For these three topics, we have already conducted sessions. So you can watch on the playlist by Prateek Mishra, most expected concept for environmental engineering, right? Today we will going to discuss a very important concept of sedimentation analysis. Okay, now my dear student, understand this. In our raw water treatment or raw water engineering, we start with water demand by calculating the total water required in the community. Once we know this water requirement, then we decide from which source we can extract this water, right? So we have the complete topic of sources of water. Once we extract this water from the source, we check the quality of water, right? Quality of water is analyzed through water quality parameters, which are of three types: physical, chemical and biological water quality parameter. Now, once we have analyzed the quality of water, we give treatment to water. The degree of treatment given to the water depends upon the existing quality of the raw water and the desired quality of the treated water. So if I talk about the different types of treatment that are given, the first treatment that is given to raw water is screening. The first treatment which is given to raw water is screening. So through screening, we remove the coarse suspended solids. Screening is used to remove coarse suspended solids. Now, how you can visualize these coarse suspended solids? For example, you are extracting water from any river, right? This river can have plants. This river can have animals. It can be living animals or dead animals, especially fishes you have, right? So in order to remove all these coarse suspended solids from the water, we go for screening. So screening is the first mechanism through which we treat water. After screening, the second mechanism of treatment is aeration. So basically, aeration is done to remove all the dissolved gases that are present in water. Aeration also removes the organic compound present in water. Aeration removes taste and odor from the water, and aeration also removes color causing compounds. But there is one drawback with aeration, that after removing the color causing compound, aeration increases the acidity of water. Aeration is the process in which water is brought in contact with the air so that exchange of oxygen from air to water can happen. And through this exchange, we increase the dissolved oxygen concentration of water. By increasing the dissolved oxygen concentration in water, we increase the chance of oxidation of organic compounds, color causing compounds, dissolved gases and other taste and odor causing compounds. So aeration basically removes dissolved gases, aeration removes color, taste and odor, and after taste and odor, it also removes the organic compounds. Okay. Now this water sample contains suspended solids. A very good evening Atul sir. Now our water sample contains suspended solids, and that suspended solids are removed by sedimentation. Those suspended solids are removed by sedimentation. Sedimentation is a process to remove suspended solids from the water. Okay. For example, this is my water sample like this. This is my water sample. And this water sample contains suspended solids like this. Okay. Now, in order to remove these suspended solids from the water, basically what we do is, we just let this water to be in the tank for some time. And when this water is still, all these suspended solids that are present in this water, these suspended solids will going to settle down. These suspended solids will going to settle under their own weight. This mechanism through which we allow these suspended solids to settle under their own weight is termed as sedimentation, right? This sedimentation mechanism is a very cheap kind of technology, right? It does not require much operational cost. That's why it is one of the most favored technique to remove suspended solids from the water. Basically, when we talk about treatment of water, it can be raw water treatment or wastewater treatment. We are talking about treating huge quantity of water. Like for tier 2 cities, the population can be more than 25 lakhs. Okay. For tier 1 cities, it is more than 50 lakhs. So the kind of water or the amount of water required to fulfill the demand of this population is huge. So whenever we are going for raw water treatment, one primary concern is that treatment should not involve much cost. Okay, so we prefer those techniques in which operational cost is less. So sedimentation is one of the technique where there is almost negligible operational cost. You allow the water to flow inside the tank, and when this water is flowing slowly inside the tank, all these solids will settle under their own weight. Now the analysis of this settling is termed as sedimentation analysis, right? Again, a very important topic. From this topic, question can be framed for sedimentation tank used in raw water engineering. From this topic, question can be framed for wastewater engineering, especially questions relating to grit chamber and primary sedimentation tank. Okay, so one single topic is helping you in 3 different ways. There are 3 different major areas from where question can be framed from this topic. Okay, so we are here that sedimentation removes suspended solids from the water. And how these suspended solids are removed? These suspended solids settle under their own weight, and hence they are removed from the water, and this water gets free from the suspended solids which are present in it. Now this settling of solids or the sedimentation of these solids depends upon one single parameter, and that is known as the specific gravity. So sedimentation, it depends on a specific gravity of the solids. The settling of these solids depends upon one single parameter which is termed as specific gravity. As simple as that. For example, this is my solid. The settling of this solid under its own weight will depend upon the specific gravity of the solids. Now, what is specific gravity? There can be n number of definitions for specific gravity, but I give you the physical relevance of specific gravity. A specific gravity of solid tells us the relative weight of this solid with respect to water, right? If the unit weight or the density of the solid is more than water, it will going to settle easily. On the other hand, if the density or unit weight of this solid is less than water, then it will going to float over the surface of water. The primary example is ice and water. The density of ice is less than that of water. That's why always you find that ice floats over the surface of the water. More the relative weight or more the unit weight of this solid, more easily this solid will settle inside the tank. So this entire mechanism of settling of solids depends upon one single parameter, which is known as the specific gravity of the solids. A specific gravity G is defined as the ratio of unit weight of solid gamma S divided by unit weight of water. Right now for us, fluid is water, okay? So specific gravity of solids is equal to unit weight of solid divided by unit weight of water. Same thing can be written in terms of density. It is equal to density of solids divided by density of water. If you talk about the standard definition of specific gravity, so G is defined as weight of solids of given volume, weight of solids of given volume divided by the weight of standard fluid of same volume. Right? Means you have the solids of some volume, the weight of the solid is W. So specific gravity G is defined as the ratio of weight of solids of some volume V divided by the weight of standard fluid of the same volume V as that of solids. For us, the standard fluid is water. So for us, this standard fluid is water. This standard fluid is water, right? Now, when you substitute the value, you can get this relation of unit weight of solid to unit weight of water or density of solid to density of water, right? You can use this relation directly, but I want you to imagine this specific gravity as the relative weight, okay? With respect to water, how heavy are the solids? If solids are more heavier than water, they settle very easily inside the water, okay? On the other hand, if solids are lighter than the water, then they will going to float over the surface of the water. Again, you can take an example of a stone and a feather, right? When you drop a stone is comparatively heavier than water, so it settles very easily. On the other hand, if you talk about the feather is lighter than water. That's why when you drop a feather over the surface of water, this feather will going to float over the surface of water, right? So the entire analysis of this sedimentation depends upon one single parameter, which is known as specific gravity of solids. A specific gravity is defined as the ratio of unit weight of solids to unit weight of water or density of solids to density of water. The basic definition of specific gravity is weight of solids of given volume divided by the weight of standard fluid of same volume. So for us, this standard fluid is water. Okay. So this is how we start with the sedimentation analysis. The first thing that we should need to understand is entire mechanism of sedimentation depends on one single parameter, that is specific gravity, which tells us about the relative weight of water, right? Now next topic of discussion is different factors which affects the sedimentation. So the first factor that affects sedimentation is turbulence. The first factor which affects the sedimentation is turbulence. So inside the sedimentation tank, where you are carrying out the sedimentation of solids, if turbulence is more, due to this turbulence, eddies are produced, okay. Inside the sedimentation tank, where you are carrying out the sedimentation of solids, due to more turbulence, these eddies are produced, and these eddies affect the settling of solids, okay. This is my solid which is trying to settle at the bottom of this tank, but due to these eddies will not allow the settling of solids. These eddies will again again send these solids back to the suspension. Okay, so whenever eddies are there, these eddies hinders the settling of solids. So in simple words, we can say that more the turbulence, lesser will be the settling of solids, because these eddies will again send back solids back to suspension. The tendency of this solid is to settle at the bottom of the tank, but due to the turbulence, due to these eddies, it is again sent back to the suspension. So more the turbulence, lesser will be the settling. More turbulence, lesser will be the settling. More turbulence, lesser will be the settling. So the first factor that affects the settling of solids is the turbulence in water. More the turbulence, lesser will be the settling. The second factor which affects the settling of solid is velocity of flow. Okay, again I'll take the example of a sedimentation tank where this sedimentation is happening. If this is my tank, right? If this is my tank, sedimentation tank, where sedimentation is happening, if velocity of flow is more, this is my velocity of flow, Vf. If velocity of flow is more, then the time available with these solids to reach bottom of the settling tank is less. So if velocity of flow is more number of solids will stay in suspension because they do not have enough time to reach bottom of the settling zone. This is one reason, right? If velocity of flow is more, available time is less for the solids to reach bottom of the settling zone. Second reason is, if velocity of flow is more, turbulence in the water will be more. And if more the turbulence, lesser will be the settling of solids. So again, you take an example of a river stream, especially in rainy season. When you have huge discharge flowing through the river stream, turbulence is more, velocity of flow is more, due to which you see a lot of suspended particles in this river. Even the river appears like muddy water, right? So whenever velocity of flow is more, you need to take care of two things. First one is, if velocity of flow is more, the time available with the solids to reach bottom of the settling zone is less, due to which settling will be less. Second, if velocity of flow is more, turbulence will be more, hence lesser will be the settling. So if velocity of flow is more, if Vf is more, lesser will be the settling. Lesser will be the settling of solids. So these two are the two primary factors which affects the settling of the solid. First one is the turbulence, second one is the velocity of flow. Now talking about the third factor which affects the settling of the solid, it is known as viscosity of fluid. The third factor which affects settling of the solids is viscosity of the fluid. Okay, so you need to take example of two tanks. In first tank, water is there, and in the second tank, honey is filled. In first tank, water is there, and in the second tank, honey is filled. So this is my water. This is water. And in the second tank, honey is there. Okay. And we know that honey is more viscous than water. Means viscosity of honey is more than water. So this is viscosity of water, which is less than viscosity of honey. Right. Now, how do you practically relate the viscosity? viscosity is related to the resistance offered against settling. If I drop a stone in both these liquids, okay, then these solids has the tendency to settle under their own weight, but viscosity of water will offer resistance against the settling of these solids. And we know that more the viscosity, more will be the resistance offered against the settling of the solids, right? Since viscosity of honey is more, so resistance offered by the honey against the settling of this solid will be more. And if resistance offered is more, settling will be less, right? So these solids have a tendency to settle like this, but this honey will going to offer resistance in the opposite direction like this. This honey will going to offer resistance in the opposite direction like this. Same goes with water. These solids has the tendency to settle like this, but due to viscosity of water, this water will offer resistance like this against the settling of these solids. So this resistance force offered in water will be less as compared to honey, right? So resistance force, Fr is resistance force. This resistance force is also known as drag force. So the resistance offered by water, resistance force Fr offered by water will be less than the resistance force offered by honey. Why? Because viscosity of water is less than viscosity of honey. If resistance offered by honey is more, then in this case, settling of solids in honey will be less. So more the viscosity, lesser will be the settling of solids. Lesser will be the settling of solids. More the viscosity, lesser will be the settling of solids. Reason is, more viscosity will offer more resistance against settling, and if resistance offered is more, settling will be less, right? So this is the third factor which affects the settling of the solid. Now fourth and the last factor which affects the settling of the solid is size of the particle. The fourth factor which affects settling of the solid is size of the particle. The fourth factor which affects settling of solid is size of the particle. For example, you have different sizes of particle like this. You have different sizes of particle like this, okay? But for all these particles, specific gravity is same. G for all the particles is same. G for all the particles is same. G is same for all particles. For all the above particles. For all the above particles. Okay, so whenever you are comparing the settling of solids of different sizes, the first thing that you need to ensure is G for all these particles should be same. Then only you can compare the settling of these solids. Okay. Now we know that if the value of G is same for all the particles, then particle with larger size will going to have more weight. And if the particle has more weight, it will going to settle down very easily, or it will going to settle down very fast. On the other hand, if the size of the particle is less, then the weight of the particle will also be less. And settling of this solid will require more time as compared to larger size particle. So if the size of the particle is different, with same value of G, particles with larger size, particle with larger size will settle easily. or will settle quickly. On the other hand, particle with smaller sizes will take some time in settling. They will going to settle in longer duration as compared to larger size of particle. Now, why I want you to consider this factor that they should have same value of G? Reason being, you take small size of stone and on the other hand, you take large size feather. G value is different for stone and feather. If you drop stone, in fact, the size of the stone is small, although it will going to settle down easily. But feather, even they have the larger size, they will going to float over the surface. So every time you are comparing the settling of solids with respect to the size, first thing you need to ensure that all the solids whichever you are comparing, those solids should have same value of G, that is specific gravity. And if all these solids have same value of G, then with respect to the size of the particle, settling will be defined. More the size of the particle, more quickly the solids will settle. Thank you so much. Thank you so much. I hope you find this session very useful. Just stay connected till the end, right? I will going to resolve all your doubts. So the fourth factor which affects the settling of the solid is the size of the particle. More the size of the particle, more easily the solids will going to settle. Okay. Now, while we are discussing about the settling of solids, you should also have an idea about this. For example, this is my water column. This is my water column like this. And inside this water column, I am allowing a solid to settle. Okay. I am allowing a solid to settle inside this water column. When you initially drop this stone inside this water column, okay. Vishnu Pandya, yes sir, okay. When you initially drop this stone inside this water column, right, there will be some turbulence. But after traveling some distance, this solid will going to settle with a constant velocity, which is known as the settling velocity of the solid. Again, I'll say this. When you drop the stone inside this water column, after some time, this stone will settle with a constant velocity, which is known as the settling velocity or terminal settling velocity, right? This settling velocity depends upon the size of the particle. More the size of the particle, more will be the settling velocity. You can imagine it very well. More the size of the particle, more quickly it will going to settle. And if it is settling quickly, it means it is settling with more settling velocity. Okay. So when you drop a particle after some time will going to settle with a constant velocity or move with a constant velocity, which is known as the settling velocity of the particle. So this Vs is settling velocity of the particle. Vs is settling velocity of the particle. Cvs is settling velocity of the particle. And this settling velocity will be constant. This is constant for a particular particle. If the size of the particle is d, the diameter of the particle is d, then for this d size of particle with specific gravity g, you will going to have only one settling velocity. If you change the size of the particle or if you change the specific gravity, then in that case, settling velocity will also change. So basically, settling velocity is the characteristic property of a particular size of particle. A particular size of particle will going to have an only one settling velocity. If you drop it in water column, right, these solids will going to settle under the constant velocity, which is known as the settling velocity of the solids. The settling velocity of the solid is calculated using the Stokes law. So next topic of discussion is your Stokes law. Stokes' law is used to calculate this settling velocity of the solids. So before starting with the derivation, there are few assumptions for the Stokes' law. First one is particles are assumed to be spherical. Okay. The only logic behind this is analysis will be easy. It is easily to calculate the volume of these particles. It will be easy to calculate the weight of these particles. So first assumption is particle is assumed to be spherical. In real terms, particles are not spherical always. They have some irregular shapes. But on general note, we start with spherical size particle. So the first assumption is particle is considered to be spherical. Second, medium is considered to be infinite. Okay. Now, you should not imagine a really infinite medium. What this statement means is sufficient space is available with this solid to settle with a constant velocity. Okay. The only thing that is related with this assumption is sufficient volume is available with the particle to settle under its constant velocity. The third assumption is settling of the particle is considered to be discrete particle settling. Okay. Now inside my water sample there will be n number of particles which are settling at same time. If this is my water sample which is present inside the tank where settling is happening, there will be n number of particles which are settling simultaneously. Now this statement means that the settling of one particle will not affect the settling of the other particle. Means if this particle is settling, the settling of this particle will not going to affect the settling of the other particles. This is what we mean by discrete particle settling. Settling of one particle will not disturb the settling of other particles. All these particles will settle separately. There is no influence of one particle over the settling of other particles. So these are the three major assumptions in Stokes' law. First one is particle is assumed to be spherical. Second one is medium is considered to be infinite. Infinite medium means sufficient volume is available for the settling of solids. Third one is settling of the particle is discrete particle settling. That is, settling of one particle will not affect the settling of the other particle. Okay. So these are the three assumptions. Now let us see the derivation for this settling velocity. So this drawn in black is my water inside which this solid is settling, and this solid is settling under its own weight. So when this solid will settle, the first force that is acting is the self weight of this solid, self weight of the solid W. Okay. This solid is settling inside this water under its own weight W. Now through Archimedes' principle, buoyant force will be acting in the opposite direction like this, force of buoyancy. Force of buoyancy will be acting in the opposite direction. The third force which is acting over this solid is, while the solid is moving down inside the water, water will apply the resistance against settling of the solid, and that resistance force is known as the drag force. That resistance force is known as the drag force, and this drag force will act in the opposite direction against the settling. This solid is moving downwards like this. So you have downward acting weight, then you have upward acting force of buoyancy, and then you have the resistance force which is again acting in the opposite direction with respect to the settling of solid. So there are three major forces that are acting over this solid, and when these three forces are in equilibrium, the net acceleration of the particle will be zero, and if net acceleration of the particle is zero, this solid will settle with a constant velocity which is known as the settling velocity of the solid. So when net acceleration is zero, this particle will settle with a constant velocity which is known as the settling velocity of the solid Vs. So I'll write down all the forces. First force is the self weight. W is self weight. W is self weight, and it is equal to unit weight of solid multiplied by volume of solid, Vs. This Vs is volume of solid. This Vs is volume of solid. Volume of solid. Okay. For settling velocity, I have taken small v. For volume of solid, this is capital Vs. Second one is the force of buoyancy. So through Archimedes' principle, force of buoyancy is the weight of water displaced by this solid. The weight of water which is displaced by this solid is equal to volume of solid multiplied by the unit weight of water. So this force of buoyancy is weight of water displaced. Weight of water displaced. This force of buoyancy is weight of water displaced, which is equal to unit weight of water multiplied by volume of solid, again Vs, capital Vs. Okay. Now third one, force of drag force, Fd. This is through the concept taught in fluid mechanics. Fd is equal to half Cd, coefficient of drag, rho W, A into Vr square. A into Vr square, right? Cd is known as coefficient of drag. So Fd is drag force. I will write here. Fd is drag force. Fd is drag force. So drag force is half Cd rho W A into Vr square. Let us see all these terms. Sir, does it comes in 4th semester and 5th semester? Yes, bacha, it comes in 5th semester. Wherever you read environmental engineering, it comes. And it is again one of the very important derivation that can be asked in your semester exam also. So observe this very carefully. Fd is equals to half Cd rho W A into Vr square. Cd is coefficient of drag. Cd is coefficient of drag. Cd is coefficient of drag. So Chandana, it is the part of environmental engineering that you read in 5th semester for raw water supplies, right? Cd is coefficient of drag. Rho W is the density of water. Now A, what do you understand by A? Understand this. You have this solid, okay? And this solid is settling like this. Over this solid, the resistance force is acting like this, which has two components, one in horizontal direction, other one in the vertical direction. So like that you have two components, one in again horizontal direction and other one in the vertical direction like this. This is your force of resistance. This is the resistance force which is offered by the water like this. Okay. This is your force of resistance which is offered by the water against the settling of this solid. This solid is settling in this direction, right? This solid is settling in downward direction. So this water will apply the resistance force perpendicular to the surface, which has two components. Now the horizontal component of these resisting force will going to cancel out each other. This component which is acting this side will cancel out by the component which is acting this side. Similarly, all the horizontal components will cancel out and only vertical components will be acting. This vertical component will act in the projected area of this sphere, okay? And the projected area of this sphere will be area of this circle, right? The projected area over which the vertical component of the resistance force will act will be area of this circle. The size of the particle is d. Size of the particle is d. So what will be the projected area? Area that I have drawn in black. Projected area A is equal to pi d square by 4. Projected area will be pi d square by 4. A is the projected area. A is my projected area, right? Now VR. VR is the relative velocity between solid and water. It is the relative velocity. It is the relative velocity between solid and water. Between solid and water, right? Now this solid is moving with a constant velocity Vs, that is the settling velocity. And velocity of water is zero, it is stagnant in the vertical direction. So relative velocity between solid and water is equal to Vs, velocity of solid, minus 0, which is the velocity of water. So this Vr comes out equal to be Vs. This Vr is equal to Vs. Okay. So this is the relative velocity between solid and water. So this is how we have defined the drag force Fd. Okay. We have defined all the forces. Now comes the physics. And physics is simple. This solid is moving with a constant velocity. It means that net acceleration of this solid is 0. And if net acceleration is 0, through Newton's second law, we know that summation of all the forces that is acting over the solid, it has to be 0. So I'll apply Newton's second law. I'll apply Newton's second law. Net acceleration is 0. Net acceleration is 0, due to which net forces acting over the solid is also equal to 0. So if net force is 0, I have self weight which is acting downward minus force of buoyancy which is acting upward minus drag force which is again acting upwards, and this should be equal to 0. Okay. Now you take Fd that side and you have W minus Fb is equal to Fd. This W minus Fb is equal to, or it's known as, buoyant weight. This is known as buoyant weight. This W minus Fb is equal to buoyant weight, right? Now substitute all the values. W is equal to unit weight of solids multiplied by volume of solids, Vs. Fb is unit weight of water multiplied by volume of solids. Fd is equal to half CD rho W projected area A, which is pi d square by 4, into Vr. Vr is Vs. Vs, which is the settling velocity of the solids. So Vs square, right? Now this volume of solids, Vs, volume of solid Vs is equal to pi d cube by 6. This is the volume of solid. It is 4 by 3 pi r cube. When you convert this r as d by 2, you will get pi d cube by 6 as the volume of solids. Now you have to substitute all the values here. Okay. One more thing, this gamma s can be written as okay, so this gamma s can be written as, it can be written as rho s into g, and similarly this gamma w can be written as rho w into g. Okay. Substitute all these values in this expression. Take Vs common from the first term. So you have Vs into gamma s minus gamma w is equal to half CD rho W. A is pi d square by 4 into Vs square, which is the settling velocity square. Vs can be written as pi d cube by 6, capital Vs, which is pi d cube by 6. This rho s can be written as gamma s into g, and this gamma w can be written as rho w into g. This is equal to half CD rho w pi d square by 4 into Vs square, right? So you can cancel out a lot of terms from this. So this is 1 times, this is 3 times. This is like d square will cancel out, so you have 1d here, and this d cancels out. Pi and pi cancels out from the either side. Okay. You take out rho w common, and that rho w will cancel out with this rho w. So I will write down all the terms. You have d by 3 into rho w. Then you have rho s by rho w minus 1 is equal to CD rho w. Then you have Vs square by 4. So this rho w and this rho w will cancel out. Rho s by rho w is equal to the specific gravity of solids, Gs, right? So this is equal to d by 3. This is equal to d by 3 into g minus 1 is equal to is equal to CD into Vs square by 4. Okay, one more thing, G is also there, you take out G also. G also you take out common, so you have G into D by 3 into G minus 1 is equals to CD into Vs square by 4. So from here you will get the expression for settling velocity. Vs is equal to under root 4 by 3 Gd into G minus 1 by CD. Mark it as very, very important expression because a lot of questions are framed from this expression, right? A lot of questions are framed from this expression of settling velocity. Vs is equal to under root 4 by 3 Gd into G minus 1 by CD. A lot of expressions are framed. A lot of questions are framed. This is the general settling velocity for a solid. Flow can be any type, okay? This expression can be used to calculate the settling velocity of the solid. Now coming to the specifics, if the flow is laminar, for laminar flow, condition, that is size of the particle d is less than 0.1 mm and second Reynolds number is less than 1. So if these two conditions are there, then for laminar flow condition, CD is equal to 24 by RE. CD is equal to 24 by RE, and this RE Reynolds number is equal to rho W Vs into D by mu. This Reynolds number is equal to rho W Vs. Vs is the settling velocity and D is the characteristic diameter, characteristic dimension, which is diameter D. Okay. So when you substitute the value of CD as 24 by RE in the previous expression, that is Vs is equal to under root 4 by 3 Gd into G minus 1 by mu by CD, by CD. Root over 4 by 3 Gd into G minus 1 by CD. When you substitute CD as 24 by RE and RE you substitute as rho W VSD by mu, you will get one more expression of settling velocity. But this expression of settling velocity will only be valid for laminar flow condition. So the expression of settling velocity for laminar flow condition is, expression for settling velocity for laminar flow condition is Vs is equal to 1 upon 18 gamma W d square into G minus 1 by mu. This is the expression of settling velocity for laminar flow condition. For laminar flow condition, Vs is equal to 1 upon 18 gamma W d square into G minus 1 by mu. So this is my expression of settling velocity for laminar flow condition. This is especially for laminar flow condition. For laminar flow condition. This is specially for laminar flow condition. Vs is equal to 1 upon 18 gamma w d square into g minus 1 by mu. This mu is known as coefficient of dynamic viscosity. Coefficient of dynamic viscosity. In many questions that are asked in GATE and even in other technical exams, what they do is, instead of giving the value of coefficient of dynamic viscosity, they give value coefficient of kinematic viscosity, nu. They give the value of nu, which is coefficient of kinematic viscosity. They give this value. Instead of giving mu, they give nu. Now, how to deal with this? Nu is equal to mu by rho. Nu is equal to mu by rho w, right? In fluid mechanics, basically you use density of fluid. For us, fluid is water, so I am directly writing rho w. Nu is equal to mu by rho w. Now you can use this expression for calculating the settling velocity. You are not seeing this rho w in this expression, but gamma w is there. Gamma w can be written as rho w into g. Then mu by rho w will be equal to nu. So this Vs is equal to 1 upon 18. Gamma w can be written as rho w into g into d square into g minus 1 by mu. Now this mu by rho w is equal to nu. So you have one more expression for settling velocity for laminar flow condition, that is Vs is equal to 1 upon 18 g d square into g minus 1 by nu. Now nu is the coefficient of kinematic viscosity. So whatever thing is mentioned in the question, accordingly you can use the expression. You will see a lot of questions, that are asked through this expression. Okay, so mark it as very, very important. So basically you have three expressions for settling velocity. First expression is the general expression. It can be used for any flow condition. Vs is equal to under root 4 by 3 Gd into G minus 1 by Cd. Second expression is only for laminar flow condition. That is Vs is equals to 1 upon 18 gamma w d square into G minus 1 by mu. If coefficient of kinematic viscosity is given to you, then you have third expression. Vs is equals to 1 upon 18 Gd square into G minus 1 by nu. Okay, it's better if you remember two expressions. One is this general expression, second one is this expression. Now by knowing this, that nu is equals to mu by rho w, you can just calculate the third expression, right? So this is again a very important part. Here g is acceleration due to gravity. Acceleration due to gravity. D is the size of the particle. D is the size of the particle. Then G is specific gravity of solids. G is specific gravity of solids. Then you have Vs, which is the settling velocity of solid. Which is the settling velocity of solid. which is the settling velocity of solid, right? So from this expression, one thing is very clear, that is the settling velocity of the solid depends on the size of the solid, and it also depends on the specific gravity of the solid. If you change specific gravity or size of the solid, settling velocity will also change. So I'll write this, and I'll write this in very bold letters. Settling of the solids depends on two things. So settling velocity Vs depends upon size of the particle, specific gravity of the particle, and viscosity of fluid, mu. Okay. So these are the three factors which can affect the settling velocity of the solids. For laminar flow condition, we have seen that for laminar flow condition, only for laminar flow condition, settling velocity is proportional to the square of size. Vs is directly proportional to d square. If you increase the size, settling velocity will keep on increasing. So settling velocity is directly proportional to d square only for laminar flow condition. For laminar flow condition, V is directly proportional to d square. Vs, that is the settling velocity of solid, is directly proportional to the square of the size. Okay. So every solid has one settling velocity, and this settling velocity depends on size of the solid, it depends upon the specific gravity of the solid, and it depends upon the viscosity of the fluid. If you change the fluid, again settling velocity will change. If you change the size of the particle, again settling velocity will change. If you change the specific gravity, again the settling velocity will change. So settling velocity is one of the characteristic property of the solid. It depends on 2-3 factors that we have just now listed, right? So this is one of the very important derivation regarding to settling velocity. Okay. Now I know the settling velocity. The next topic of discussion is the sedimentation tank. So the tanks in which the sedimentation of the suspended solid is done are termed as sedimentation tanks, right? The tanks in which settling of the solids are done are termed as sedimentation tank. These sedimentation tanks are of two types. First type of sedimentation tank is known as quiescent type sedimentation tank or fill and draw type sedimentation tank. The tanks in which settling of solids is carried out is termed as sedimentation tank. These sedimentation tank are of two types. First one is known as quiescent type sedimentation tank and fill and draw type sedimentation tank. The first type of sedimentation tank is quiescent type or fill and draw type sedimentation tank. Now, this is a very simple tank. Basically, what we do is, we fill this water in this tank for 24 hours. We fill the water for 24 hours. We fill the water for 24 hours. In these 24 hours, the suspended solids which are present in water, they will undergo settling. In these 24 hours, the suspended solids which are present in the water, they undergo settling like this. They undergo settling like this. And these solids are collected in the sludge zone. These solids, when they reach bottom of the tank, they form a mixture with water which is known as sludge. And these solids are connected in the form of sludge. So the solids which are settled solids plus water, they form sludge. So what is sludge? Sludge is basically a mix of these settled solids along with water. They form slurry, right? Thick slurry, which contains a lot of these settled solids, which are removed from the water. So this solids settle at the bottom of the tank, and this bottom zone is known as the sludge zone, from where these solids are removed from the system. The space in which the settling of solid is taking place, this space is known as settling zone. So this tank is broadly divided into two compartments. The upper compartment where settling is happening is known as the settling zone, and the bottom compartment where the slurry is collected, that is known as the sludge zone. Then this sludge is removed either manually or mechanically. So what we do in this tank is, we fill the water for 24 hours. In these 24 hours, these solids will going to settle and they form slurry at the bottom, which is known as sludge. This slurry is collected in the sludge zone and then it is removed from the system either manually or mechanically. After 24 hours, when all these solids settle out, this water is drawn from the tank. This water is drawn from the tank. That's why the name is given fill and draw type sedimentation tank. We fill the water for 24 hours, solids settle in the tank for 24 hours. Then after 24 hours, we take out this water. This water that we take out is known as settled water. Reason is, we have allowed the solids present in the water to settle for 24 hours. Okay. So every time, anytime if you have this term in your exam, like what is settled water? Settled water is that water in which sedimentation has already taken place. So this water which is drawn out, it is known as settled water. This water is known as settled water. This water is known as settled water. The water which is drawn out after settling of the solids, it is known as settled water, right? The cleaning of this sludge can be done in two ways. Cleaning of sludge zone or cleaning of sludge can be done in two ways. First is, it can be done either manually. It can be done either manually or it can be done mechanically. It can be done either manually or it can be done mechanically. Whenever we are cleaning this sludge manually, a sludge zone will be provided. Okay. And when this cleaning is done mechanically, this sludge zone is not provided. Instead, we provide a slant. So these solids settle in the settling zone. These are my solids. These are my solids which are settling in the settling zone. These are my solids which are settling in the settling zone like this. And these solids will reach the bottom of the settling zone. These solids will reach the bottom of the settling zone from where they are removed mechanically. From where they are removed mechanically like this. These solids are removed mechanically out of the system like this, right? So whenever you are going for mechanical cleaning of this sludge, only settling zone is provided. Only settling zone is provided. This is my settling zone where settling of solids is happening. This is my settling zone. So whenever cleaning is done mechanically, a sludge zone is not provided. A sludge zone is not provided, right? Now for obvious reasons, since these type of tanks a lot of time to remove the suspended solids, like they take 24 hours to remove suspended solids from the water, hence they are never used to treat community water. Because if you just calculate or if you just have an idea how much water is required even for tier 3 cities, which are having 10 lakh of population, that water is huge. And if we need to construct tanks to hold this water for 24 hours, the length of the tanks will come in kilometers. And practically, providing tanks in kilometers is not possible. So these type of tanks are not used to treat community water for tier 3, 2 and 1 cities. They can be used to treat water for small community, or they can be used to treat water for a local village, right? They can be used to treat water where population is less. So these are the first type of tanks not used to treat community water. Reason is they require a lot of time, like they require 24 hours to remove the solids from the water. That's why they are not provided for treating the community water, Two things to remember from this. First type of tank is quiescent type tank or fill and draw type tank. We fill the water for 24 hours. In these 24 hours, solid will settle at the bottom of the tank, and after that, the water is drawn out. This water which is drawn out is known as settled water. The zone in which settling happens is known as the settling zone, and below settling zone, where this sludge is formed, it is known as the sludge zone. If cleaning of the sludge is done manually, then sludge zone will be provided. But if cleaning of the sludge is done mechanically, the sludge zone is not provided. Instead, we provide a slant over which these solids come and settle, and through mechanical equipments, we just scrap all this sludge which is formed at the bottom of the settling zone. Okay. So these are the important points for this type of tank. Okay. From exam point of view, not that much important. Important is the next tank that we will going to discuss. The second type of sedimentation tank is known as continuous flow type sedimentation tank. Is known as continuous flow type sedimentation tank. This is the very important tank. Reason is practically we provide these type of tank to treat community water. Practically, we provide these type of tanks to treat community water. Okay, so the next point of discussion is continuous flow type tank. So as the name says, continuous flow type, it means that inside these tank, we maintain the continuous flow of water. Okay. Now in the direction this flow is maintained, based on that, these continuous flow type tanks are again subdivided into two categories. First one is known as the horizontal flow type tank. If the direction of flow is along the horizontal plane, then it is known as horizontal flow type tank. So if the direction is flow is along the horizontal plane, then this is known as the horizontal flow type tank. If the direction is flow in the vertical direction, then that type of tank is known as the vertical flow type sedimentation tank. If direction is flow is in the vertical direction or along the vertical plane, then they are termed as vertical flow type sedimentation tank. Okay. So continuous flow type sedimentation tanks are those tanks in which we maintain the continuous flow of water. If the direction of flow is along the horizontal plane, then they are known as horizontal flow type tank. If the direction of flow is along the vertical plane, then they are known as vertical flow type tank. We will start with the horizontal flow type tank. We start with horizontal flow type tank. Okay, so before starting this, I would like to discuss something else. This is my horizontal flow type tank. How we have defined horizontal flow type tank? Horizontal flow type tanks are those tanks in which we maintain the horizontal direction of flow. So water is basically entering from this end like this, and it is flowing in the horizontal direction like this. This is my velocity of flow. This is my velocity of flow Vf. This is my velocity of flow like this, Vf. This is my velocity of flow Vf, okay. So if the flow is maintained in the horizontal direction, it is known as the horizontal flow type tank, okay. Now inside this tank, suspended solids are present of all sizes. Suspended solids are present of all sizes like this. Literally, this is not the size of suspended solids. I have just enlarged the picture, right? Those suspended solids are tiny particles. But just to give you an idea, suspended solids of all the sizes are present inside the tank. The sizes of these suspended solids are different. Say this is D1, this is D2, this is D3, this is D4. Right? These are the sizes of the suspended solid. Corresponding to the size of the suspended solid, all of them will going to have different settling velocity. This is Vs1, this is Vs2, this is Vs3, this is Vs4. Okay. Why we are providing these tanks? These tanks are provided to settle out suspended solids. Now when we talk about water sample, it contains particles of all the sizes, starting from the finer size particle to the larger size particle. With the changing size, all these particles will going to have different settling velocity. With respect to these settling velocity, all the particle, if they want to settle inside the tank, they need to cover this distance of capital H, which is the height of the settling tank. All of them needs to cover this vertical distance capital H. Okay. All the particles which are entering inside the tank, in order to reach the bottom of the settling zone, they have to cover this distance of capital H. If the settling velocity is less, time taken by the particle to reach the bottom of the settling zone will be more. On the other hand, if settling velocity is more, time taken by these particles to reach the bottom of the settling zone will be less. Now the question comes, do we design these tanks to remove all the particles? No, we do not design these tanks to remove all the particles. Reason is, for suppose this is the smallest size of particle which is present. With respect to this size, settling velocity will be Vs1. Okay. Now with this settling velocity, the time required by the particle to reach the bottom of the settling zone will be very large. With this small settling velocity, the time required by the particle to reach the bottom of the settling zone is very large. And if we need to provide such time for this water to stay inside the tank, the length of the tank that we need to provide is huge. Okay, how we are providing time for particle to settle? By giving a lot of length to the sedimentation tank. As the water starts from this point, as the water starts entering into the tank from this point, this is the time which is taken by the water to reach from this end to this end. And this is how we are providing time for solids to settle inside the tank. If the solid is of smaller size, and if we are designing the tank for the removal of the smallest size of the particle, then I have to provide a lot of time to this water. And how we are providing the time? By increasing the length of the tank. Okay. So sometimes what happens is, removal of this particle requires a lot of time. And for providing this time, the length that we calculate, it again comes out in kilometers. If we need to provide such a large time to this water or for the particles to settle, we have to provide lengths in kilometers. That's why we do not design these tanks for the removal of all the suspended solids, right? Especially the finer suspended solids. So we as an engineer, we take one size of the particle. Based on our experience, we take one size of the particle. Say I have chosen this size of the particle. Okay. Now I will design this tank for the removal of this size of particle. That is, I provide this much length to the tank so that sufficient time is available to this particle to reach bottom of the settling zone. This particle for which this sedimentation tank is designed is termed as concerned size of the particle. This particle for which the sedimentation tank is designed is termed as concerned size of the particle. So this size of the particle for which the sedimentation tank is designed. So size of the particle for which sedimentation tanks are designed. Size of the particle for which sedimentation tanks are designed is termed as concerned size of the particle. Is termed as concerned size of the particle. So that particular size of the particle for which a particular sedimentation tank is designed is termed as concerned size of the particle. Now what do we mean by designing the tank with respect to the size of the particle? It simply means we are providing adequate length that will give sufficient time to this particle to reach bottom of the settling zone. As simple as that. That is what we mean by designing the sedimentation tank with respect to the particular size of the particle. So if we are designing this tank with respect to this concerned size of the particle, so this is my tank like this, right? This is my tank and my solid particle is entering from here. This is the entry point from where the solids are entering. And this is the exit point of water. Water is flowing with the horizontal velocity Vf. Okay. This is the size of the particle. Say this size is d, which is the concerned size of the particle. Concerned size of the particle. Concerned size of the particle, right? This is the particle for which we are designing this tank. Okay. If you observe this particle, its horizontal velocity is Vf and its settling velocity is Vs. Vs is the settling velocity and Vf is the horizontal velocity. Now what do we mean by designing the tank with respect to this size of particle? It means that sufficient time we are providing to this particle to reach bottom of the settling zone, right? This is my settling zone. This is my settling zone. This is my settling zone. The height of the settling zone is capital H and length of the tank is L. Length of the tank is L, like this. Length of the tank is L. And below this, we provide the sludge zone. Below this, we provide sludge zone. This is the sludge zone. Right? So what do we mean by designing the tank with respect to the concerned size? We mean that we are providing sufficient time to this particle and that time is Td. We are providing sufficient time to this particle so that this particle will reach the bottom of the settling zone. Now the time taken by this particle to reach bottom of the settling zone is equal to h divided by Vs. Vertical distance is capital H and the velocity which is responsible for covering this distance is Vs. Now, in the same time Td, this particle will flow with the horizontal velocity Vf. In same time Td, this particle will cover the horizontal length L. So for this same time Td, it will going to cover horizontal length L with velocity Vf. That is what we mean by designing the sedimentation tank with respect to concerned size of the particle. That in the given time or in the available time, this particle will move down by the amount of h, and the same time it will move along the length, the value of which is equal to L. So if you want to track how this particle will travel, since this particle has two velocities, so it will travel like this. It will travel like this. It will travel like this, right? This particle will move horizontally with velocity Vf and will move downward with velocity Vs. And this particle moves like this diagonally, right? So this is what we mean by designing the sedimentation tank with respect to the concerned size of the particle. The size of the particle for which the sedimentation tanks are designed is termed as concerned size of the particle. And what do we mean by designing the tank? It means that we are providing sufficient time Td so that this particle can travel a distance of capital H and a distance of capital L with velocity Vs and Vf respectively. Okay. So this is how concerned size of the particle travel inside the tank. It starts from one corner and it reaches the opposite corner while traveling this length L. At the same time, it also travels this height of capital H. Okay. So this is how we design the sedimentation tank with respect to the concerned size of the particle. Now with respect to this, I would like to define few terms. First one is Td. Td is known as retention time. Td is known as retention time or detention time. Or detention time. This Td simply tells us about by how much time, by how much amount of time water is staying inside the sedimentation tank. Td also tells us about how much time is available with the solids to settle inside the sedimentation tank. So Td is the time for which, water stays inside sedimentation tank. Td is also the time available with solids. Time available with solids or time available to solids to settle in the sedimentation tank. To settle in the sedimentation tank. To settle in the sedimentation tank, right? Most of the students have this confusion. What is Td? Td is nothing but the retention time or detention time. It is the time for which water stays inside the sedimentation tank. When you observe this flowing water, right? When you observe this flowing water, this water is entering from this end. In Td time, it will going to reach this end. In Td time, this water will going to reach this end. So the time available with the solids to settle inside the tank is Td. Okay. and that time is calculated with respect to the concerned size of the particle. That time TD is calculated with respect to the concerned size of the particle. TD is the time required by the concerned size of the particle to reach bottom of the settling zone. And this time TD we provide by providing length of the tank. Okay. So this is how we design this sedimentation tank. If you observe this sedimentation tank, again you can write down the dimensions. Okay. So this is my longitudinal section and that is my cross section of the horizontal flow type tank. So length of the tank is L. Length of the tank is L, and this is known as the settling zone. This is known as the settling zone. Then you have the sludge zone. Then you have the sludge zone. The height of the settling zone is capital H. The height of the settling zone is capital H, right? Now when you cut this cross section for this tank, this is the height which is visible, capital H. And the width of the tank is capital B. This is the width of the tank, and again this is my sludge zone. This is the sludge zone and this is my settling zone. This is sludge zone and this is my settling zone, right? Okay. So when you observe this, what can be this cross-sectional area? The cross-sectional area is, I'll write here, cross-sectional area is H into B. Cross-sectional area is H into B. When you observe this tank from the top, plan area will be L into B. Plan area will be L into B. Is L into B, right? So I think these geometry of this sedimentation tank is clear in your mind. When you take the longitudinal section, length will be visible and height of the settling zone is visible. When you take the cross section for this tank, this height of the settling zone is visible and the width of the tank is visible. Now we have seen this, TD is equal to H upon Vs, and it is also equal to L upon Vf. Okay. Now discharge which is flowing through the tank, this discharge which is flowing through the tank is equal to velocity of flow Vf multiplied by this cross-sectional area, right? The velocity Vf will be perpendicular to this cross-sectional area. So discharge flowing through the tank is equal to velocity of flow multiplied by the cross-sectional area. This cross-sectional area can be written as H into B, okay. Now when you substitute this Vf in terms of Vs, so this Vf can be written as L into Vs divided by H. And when you substitute this Vf, you have Q is equal to L into Vs into H into B divided by H. So this H and this H cancels out. You have L into B. You have Q is equal to L into B multiplied by Vs. This L into B is nothing but the plan area. So this is one of the way for calculating the settling velocity of the concerned size of the particle, which is equal to discharge divided by plan area. So Vs is equal to discharge divided by plan area. Vs is equal to discharge divided by plan area, right? Now observe this very carefully what I am saying. Vs is the settling velocity of the concerned size of the particle for which we have designed the tank. Vs is settling velocity of concerned size of the particle Vs is the settling velocity of concerned size of the particle for which we have designed the tank. This Vs is known as surface overflow rate. This is known as surface overflow rate. This Vs is known as surface overflow rate. Only the settling velocity of the concerned size of the particle for which we have designed the tank is known as surface overflow rate. So what is surface overflow rate? It is the velocity, settling velocity of the concerned size of the particle for which we have designed the tank. So surface overflow rate is the settling velocity of concerned size of the particle for which we have designed the tank. So for every tank, there will be only one surface overflow rate. And that surface overflow rate is nothing but settling velocity of the tank, settling velocity of the particle of concerned size. So whenever surface overflow rate or SOR is written, this can be simply related with the settling velocity of the concerned size of the particle. And this concerned size D is that size of the particle for which we have designed the sedimentation tank. Okay. So surface overflow rate is nothing but the settling velocity of the concerned size of the particle. Okay, I think this is pretty much clear to you because in many questions directly it will be mentioned as surface overflow rate. So you have to remember this, surface overflow rate is nothing but the settling velocity of the concerned size of the particle for which we have designed the tank. Okay, so this surface overflow rate is equal to discharge divided by plan area. This surface overflow rate is discharge divided by plan area. This surface overflow rate is equal to discharge divided by plan area. So you can see a lot of questions that are asked using this expression also. So whatever we are discussing is very important related to gate preparation. So whatever is written in the board, every word is important. Okay. Now we will analyze these tank with respect to other size of particles. For that analysis, we need to have these two assumptions. First assumption is concentration of particles of all the sizes is same at all the points of the vertical section at the inlet end. It means this is the section from where water is entering into the tank. This is my section, this is my vertical section. This section contains particles of all sizes, and these particles are uniformly distributed along the full depth of the settling zone. What this assumption means? At the inlet section, at this section, particles of all the sizes are uniformly distributed. Particles of all the sizes are present, and all these particles are uniformly distributed at this inlet section. Okay. Now, second assumption is a particle is assumed to be removed only if it reaches bottom of the settling zone. Means only if the particle reaches bottom of the settling zone in the given time, then that particle is assumed to be removed. I'll give you one example. I'll give you one example like this. For example, this is my tank. This is one size of particle. This is one size of particle, right? And this particle is reaching here itself in the given time. This particle is reaching at this point in the given time that is available for the settling of solids. Since this particle is not reached the bottom of the settling zone, hence we will not consider this particle to be settled, right? Or we do not consider this particle to be removed from the system. Particle will only set to be removed if it reaches the bottom of the settling zone. If it reaches the bottom of the settling zone, like this particle. This particle which is traveled this much distance to reach here, this particle is not set to be removed. It is not set to be removed. Only particle which reach bottom of the settling zone are set to be removed. So this is considered not removed. This is considered not removed. And this particle is removed. And this particle is removed, right? This particle is considered to be removed. Okay. Now starting with my analysis. First one is case 1. Concerned size of the particle D present at height small h. Concerned size of the particle D present at height small h. So this is my sedimentation tank where the particle is present at some height small h. This is my sedimentation tank. This is the concerned size of the particle. This is the concerned size of the particle present at some height small h, like this. This is the settling zone that I am drawing, right? This is the smaller size of particle present at some height small h. Okay. This particle is having horizontal velocity Vf and it is having vertical velocity Vs. It will settle with velocity Vs. Okay. Now if you consider this particle, concerned size of the particle which is present at height capital H, we have provided sufficient time for this particle to reach bottom of the settling zone. We have provided sufficient time for this particle to reach bottom of the settling zone. So I'll take this as the basis. Okay. This will be the basis of my analysis. Concerned size of the particle present at height capital H will move with the horizontal velocity Vf and will move with the vertical velocity Vs. Okay. Now, with respect to this particle, the same size of particle present at height small h. So this particle has to travel height small h to reach bottom of the settling zone. So time taken by this particle is T1. And this time is the time required by this particle to reach bottom of the settling zone, which is h by Vs. Okay. Now, sorry, this is small h by Vs. Small h by Vs. Now we know that small h is less than capital H. So this T1 will be less than Td. Means whatever time is available to this solid, in lesser time, it will reach bottom of the tank. Okay. Now in this time T1, the length travelled by the particle is equal to, length L1 travelled by the particle is equal to T1 into Vf. Since this T1 is less than Td, therefore this length L1 travelled by the particle is also less than L. This L1 is less than L, right? So when you take down these two, this particle will going to travel like this to reach bottom of the tank. And this settling will be parallel to this settling, okay? So all the particles of concerned size, it doesn't matter at whatever height they are present, all the particles will be removed from the system. So concerned size of the particle present at height small h will be removed from the system, and concerned size of the particle present at height capital H will also be removed from the system, because all these particles are reaching bottom of the settling zone in the available time Td. Okay. In fact, if this concerned size of particle is present at some smaller height, it is reaching bottom of the settling zone early. So this is Vf and this is Vs. The length travelled by this particle, this is L1. The length travelled by this particle is L1, which is clearly less than L. Okay. So this is my case number 1. In case number 1, we have discussed that concerned size of the particle, it doesn't matter whether it is present at capital height H or at height small h, all the concerned size of the particle will reach bottom of the settling zone in the available time Td. So all the concerned size of the particle are 100% removed. So concerned size of the particle, concerned size of the particle are 100% removed. Concerned size of the particle are 100% removed. Okay, this is my case number 1. Now case number 2 is, I will take larger size of particle which has size more than the concerned size. Larger size of particle, case 2. Larger size of particle d dash which has more size than the concerned size present at height capital H. Present at height capital H. Okay. So again I draw this tank. So this is my concerned size of the particle. This is my concerned size of the particle d. And again I'll draw this, how it reaches the bottom of the tank. This is how it reaches the bottom of the tank. This is my concerned size of the particle d. Velocity of flow Vf and vertical velocity is Vs. Okay. This is how it reaches the bottom of the tank like this. Now, if at the same height capital H, bigger size of the particle is present, which has size more than the concerned size. Okay. At the same height capital H, if I have the particle which has more size, for this bigger size of particle, horizontal velocity of flow is same because Vf is the velocity of water through which all the solids will travel along the horizontal direction. But now the settling velocity Vs dash will be more than Vs. Vs dash will be more than Vs. Okay. Now the time taken by this particle to reach bottom of the settling zone, it will be less than Td because Vs is more than Vs. Sorry, Vs dash is more than Vs. So time taken by this particle to reach bottom of the tank is equal to capital H by Vs dash. Since Vs dash is more than Vs, so this T dash will be less than Td. That is the time available with the solids to settle inside the tank. So in the given time, even in lesser time, these larger size of solids will going to settle in the tank. In this time T dash, the length traveled by the particle L dash is equal to T dash into Vf. Okay. Now this T dash is less than Td, therefore this L dash is less than L. So this particle will travel like this. This particle will travel like this. This is how this particle will travel. This is how this particle will travel. Horizontal velocity is Vf and vertical velocity is Vs dash. The length traveled by the particle is L dash. And clearly it is visible that this L dash is less than L. So in less time, this larger size of particle will reach bottom of the settling zone. This larger size of particle will reach bottom of the settling zone. Even in the lesser time, this larger size of particle will reach bottom of the settling zone. Now if this larger size of particle is present anywhere in this height, they will reach bottom of the settling zone in lesser time. So particles of size more than the concerned size, they are also 100% removed. If you consider same particle at this height, at some smaller height, right? This will also travel like this and reach bottom of the settling zone. So larger size of particle, it doesn't matter if they are present at capital H height or at height some small h, all these particles are reaching the bottom of the settling zone in the given time. Hence, all these particles are considered to be removed. So particles of size larger than the concerned size, are 100% removed. Larger than the concerned size are 100% removed. So till now, two sizes of the particle. One is the concerned size and second one is the size more than the concerned size. All these particles will be removed completely from the water in the available time TD. Okay. So whenever we are designing this horizontal flow type tank, concerned size of the particle and particle having size more than the concerned size are 100% removed from the water. Okay. Now third case, particle of size lesser than the concerned size present at height capital H. Case 3. Particles of size d double dash lesser than the concerned size present at height capital H. Okay. So again I'll draw this tank. This is my tank. This is my concerned size of the particle, and this concerned size of the particle is settling like this. This concerned size of the particle is settling like this. This concerned size of the particle is settling like this. It is moving with the horizontal velocity of flow Vf and vertical velocity of flow Vs. Okay. This is my concerned size of the particle. Using this, we are doing all the analysis. Now, if I have the smaller size of particle, this is my smaller size of particle. This is my smaller size of particle which is present at height capital H. This is smaller size of particle present at height capital H. For this smaller size of particle, horizontal velocity of flow is Vf and vertical velocity of flow is Vs double dash. Vs double dash is the settling velocity of the particle of size smaller than the concerned size. Now observe this very carefully. This settling velocity of smaller size of particle will be less than the settling velocity of concerned size of the particle. It means that Vs double dash is less than Vs, which is the settling velocity of the concerned size of the particle. Okay. Due to which the time required by this smaller size of particle to reach bottom of the settling zone will be more. So the time required by this particle to reach bottom of the settling zone is h by Vs double dash. Since this Vs double dash is less than Vs, due to which this T double dash will be more than Td. This T double dash will be more than Td. It means that time required by the smaller size of particle to reach bottom of the settling zone is more. But that much amount of time we are not providing to this water or the solids to settle. So in the available time Td, these solids will not reach the bottom of the settling zone. In fact, the path travelled by them is like this. The path travelled by the smaller size of particles is like this. The path travelled by the smaller size of particle is like this. This is the path travelled by the smaller size of particles. This is the path travelled by smaller size of particles, d double dash. You can clearly observe that this smaller size of particle haven't reached the bottom of the settling zone. Therefore, these particles are not considered to be removed. A particle is only considered to be removed if it reaches the bottom of the settling zone. This particle haven't reached the bottom of the settling zone. It moves with horizontal velocity Vf and with settling velocity Vs double dash. And Vs double dash is clearly small than Vs. So the particles of smaller size present at height capital H are not removed from the system. So you can write down particles of smaller size present at height capital H are not removed. Present at height capital H are not removed, right? So right now we know about three particles. First particle is the concerned size of the particle, which is getting removed in the available time Td. Second one is the larger size of particle. Larger size of particle is taking less time from getting removed from the system. Available time is Td, larger size of particle is taking lesser time this Td to getting removed from the system. Third one is the smaller size of particle present at this height of capital H. In the available time Td, these smaller size of particles are not reaching the bottom of the settling zone. They are reaching at this height. They are only covering this much amount of height in the available time Td. That's why these smaller size of particle are not considered to be removed that are present at height capital H. Okay. Now case number 4. Case 4. A smaller size of particle d dash less than d present at height small h. Present at height small h. Present at height small h. Okay, so let me draw this. So this is my concerned size of the particle present at height capital H and covering the distance in the available time. Okay. Now observe this very carefully. This is Vf and this is Vs. Length of the tank is L and height of the tank is capital H. Height of the settling zone is capital H. This is capital H like this. Now what this case is saying, that smaller size of particle, this is the smaller size of particle. This smaller size of particle is present at height small h. This smaller size of particle d double dash is present at some height small h. This is smaller size of particle d double dash. This is the concerned size of the particle d, right? Now this height small h is such that in the available time Td, the smaller size of particle can cover this height small h. Okay, this small h height is such that in the available time Td, these particles are covering this height of small h. Means in available time Td, the smaller size particle is covering this height of small h. Vs double dash. Okay. Then in this available time Td, the horizontal length covered by these particle L will be equal to Td into F, Td into Vf. So this is such height at which these particles are present that in the available time Td, these particles are able to cover this small height h. So when you draw the path travelled by these particles, it looks like this. So this is the path travelled by the particles. This is the path travelled by the particle, right? This particle started from this height and in the available time Td, it has reached the bottom of the settling zone like this. The horizontal velocity is Vf and the vertical settling velocity is Vs double dash. In the available time Td, these particles are managing to reach the bottom of the settling zone. Since these smaller size of particle which are present at this height small h are reaching the bottom of the settling zone in the available time Td, that's why we say this, these smaller size of particle are partially removed. The smaller size of particle present at this height small h will be removed. If it is present at some other height below this, it will again be removed like this. If it is present at some height even less than this, it will always be removed. So whatever smaller size of particle which are present in this zone, they are completely removed. But all the smaller size of particles which are present above this height, they will not reach the bottom of the settling zone in the available time Td, and that's why we say this. Smaller size of particle are partially removed. Smaller size of particle up till height small h will be removed from the system. But if they are present above this height, then there in this zone, the smaller size of particle will not reach the bottom of the settling zone. Hence, they are not considered to be removed. So, smaller size of particle present up to small h height, are removed. And if the same smaller size of particles, if they are present above this height, they will not reach the bottom of the settling zone in the available time Td, and that's why we say this, that these particles of smaller size above this height will not be removed. So smaller size of particles are said to be partially removed. So we'll write this. So D, concerned size of the particle, they are 100% removed. They are 100% removed. D dash, particles of size greater than the concerned size, they are also 100% removed. They are also 100% removed. But particles which are having size lesser than the concerned size, they are partially removed. They are partially removed. That is up to height small h. They are partially removed, right? Now this small h height is corresponding to the particle of size d double dash. As the size of the particle will change, this height small h will also keep on changing. Okay, that's why all the smaller size of particles, they have different percentage removal. Smaller size particle have different percentage removal. That how much percentage of smaller size of particle are removed. Particles of size equal to and more than the concerned size are completely removed, but the smaller size of particle, they have the partial removal. And this percentage removal of smaller size of particle, percentage removal of smaller size of particle, percentage removal of smaller size of particle smaller size of particle is equal to small h by capital H into 100, or this is equal to settling velocity of the smaller size of particle divided by the settling velocity of the concerned size of the particle into 100. So these are the two formulas from which you can calculate the percentage removal of the smaller size of particle, which is small h by capital H into 100, or which is equal to Vs double dash, which is the settling velocity of smaller size of particle, divided by Vs into 100. So Vs double dash is the settling velocity of particle of size d double dash. On the other hand, Vs is settling velocity of concerned size of the particle, settling velocity of concerned size of the particle, settling velocity of the concerned size of the particle, and this is also known as surface overflow rate. It is also known as surface overflow rate. In GATE 23, we have seen question. In GATE 22, we have seen question from the same concept. Okay. So this is a very important concept of percentage removal. Percentage removal of smaller size of particle is small h by capital H into 100, or Vs double dash by Vs into 100. This is very important. Now, only if the flow is laminar, the percentage removal can be calculated using one more expression. For laminar flow condition, we have seen that settling velocity is directly proportional to the square of size of the particle. So only for laminar flow condition, percentage removal can be calculated using the size of the particle. So this is equal to d double dash square divided by d square into 100. Only for laminar flow condition, percentage removal is equal to d double dash square divided by d square into 100. Only for laminar flow condition. Okay. Only for laminar flow condition this can be done. Only for laminar flow condition. Next is efficiency of sedimentation. Efficiency of sedimentation can be calculated as the product of percentage concentration So efficiency of sedimentation is equal to percentage concentration multiplied by percentage removal. efficiency of sedimentation is equal to percentage concentration multiplied by percentage removal. So this is how you calculate the efficiency of sedimentation, which is nothing but percentage concentration multiplied by the percentage removal, right? So these are some of the very, very important concepts regarding sedimentation analysis. Okay. I hope you have found this session very informative. If I talk about the horizontal flow type tank, in horizontal flow type tank, concerned size of the particles and particles having size more than the concerned size are completely removed. Particles of size less than the concerned size are partially removed. Second important point. The settling velocity of the concerned size of the particle is known as surface overflow rate, which can be calculated as discharge divided by the plan area. Okay. So all these analysis can be used to solve questions, especially that are asked in GATE examination. When you see the previous year GATE questions, you will find a lot of questions that are framed using these concepts. Concept of settling velocity, concept of how designing this horizontal flow type tank through concerned size of the particle. All these concepts are very important. And the best thing is, we at IMS GATE Academy is providing you with the crisp and precise content in order to excel and perform very well in your upcoming GATE examination and even for the other technical exams. You can join our Telegram group. The link is given in the description box for daily quizzes, for different sessions that we are conducting. You can always check to our website for different courses that are available. We are providing you with zero fee program where we are not charging a single penny and we are giving you free lectures along with the content. We at IMS GATE Academy are ready to help you if you are serious about your GATE preparation or the preparation of other technical exams. So I, Prateek Mishra, signing off for today, and I'll meet you in the next very interesting session of the most expected concept series for environmental engineering. Stay tuned to our channel. Please like and subscribe the session. Please like and subscribe the channel and please share the session as much as possible. Thank you so much for listening patiently. Have a very good night ahead. Thank you so much.